All right, so now we're going to be looking at a slip ring induction motor problem. And the problem says that we have a three-phase 50 Hz induction motor with its rotor star connected. Gives 500 volts at standstill between the slip rings on open circuit. Now there's two keywords here, standstill and open circuit. When it says that the motor is at standstill and on open circuit. So let's look at the picture quickly. So when it's at standstill, it means that the rotor is not moving. It's the instant that the motor is turned on, and this rotating magnetic field of the stator is moving at 50 Hertz, and all of that is cutting the rotor because it's standing still. And when it says it's open circuit, it means that these three resistors are connected to each of these phases. So the impedance of one phase would be the impedance of this coil and the impedance of that external resistor. All right, so that's on open circuit, and that's at standstill. So when it's on short circuit, which is the second part of the problem, it means that this contactor in front of these resistors are closed, and these three resistors are removed from the circuit. They shorted out, so they removed from the circuit. And then the only impedance we have left is the impedance of each of these three coils. Okay, so remember, when it's on open circuit, we have the impedance of the coil and the resistor. When it's on short circuit, we have the impedance only being the coil. All right, so let's get back to the problem. So we see here, calculate the current and the power factor at standstill when the rotor windings is joined to a star connected external circuit. And that means that the rotor is connected to this external resistors, each phase of which has a resistance of 10 ohms and an inductance of 0.04 henries. Okay, so that's what each external resistor has, 10 ohms and 0.04 henries. All right, so the reason why it's got a inductance as well is because if you see one of these resistors in real life, it looks like a cylinder that is wound with a coil. All right, so it's got a small inductive reactance, but it's a larger resistance. All right, so it has got an inductance. The resistance per phase of the rotor windings is 0.2 ohms, and its inductance is also 0.04 henries. Okay, so in this problem, it just happens that both the external resistor and the rotor phase has the same inductance. And then it says also calculate the current and the power factor when the slip rings are short circuited and the motor is running with a slip of 5%. Okay, so that's the second part of the problem, when the motor is up and running and the external resistors are then removed from the circuit because it's at short circuit and these are taken out of the circuit. Okay, and when it says it's at 5% slip, that means that this stator is still going at 50 Hertz, the rotating magnetic field, but the rotor is going at 95%, so 5% slower than the rotating magnetic field. Okay, so it means that the rotor is only at full speed, it's only experiencing 5% of this rotating magnetic field, and we'll see how that impacts the problem. Okay, so let's start with the phase voltage. Okay, so they said that the rotor gives 500 volts between the slip rings, so that is the line voltage. So we're going to change that to phase. So we're going to divide the 500 volts divided by square root 3, and we get 288.67 volts. Okay, so that's the phase voltage of each phase. All right, then they gave us the inductance of the rotor coil, the rotor winding, and they gave us the inductance of the external resistor. And it's the same inductance for both. So the inductive reactance of the rotor we calculate by using 2 pi FL. So 2 times pi times 50 hertz times the inductance, and we get 12,57 ohms. So that's the inductive reactance of the rotor coil. Then the inductive reactance of the external resistor, also 2 pi FL. So 2 pi times 50 times 0,04, and we also get 12,57. Right, so that's of the external resistor. Then, like we said in the previous picture here, how do we get the impedance? So we're going to say the impedance of the coil plus the impedance of the external resistor. So to get the total impedance on open circuit at standstill. So here I've bracketed this off. You can see here this is the rotor plus the external resistor. So they gave us the resistance of the rotor winding, and we just calculated the inductance, the inductive reactance of the rotor winding. And then over here they gave us the resistance of the external resistor was 10 ohms, and we calculated the inductive reactance of the external resistor. So then we add that up in rectangular form and we change it to polar form. All right. So that now is the total impedance of the rotor winding and the external resistor. Then next we have to work out the current, right? The current for each phase. And that is just the phase voltage, right, which we got as 288,67 divided by the total impedance. So that's the rotor winding plus the external resistor. And that is just 288,67 divided by 27, and we get the current in the phase. The power factor is just power factor equals cos phi, and we have the phase angle 67,92, and then we can calculate the power factor with the external resistors engaged. All right, in the next part of the video we're going to look at the short circuit part, so when the resistors are shorted out of the circuit.